Hello, my name is Jia Jung, a graduate student at University of Houston. I will talk about changes in ozone chemical regime over the contiguous United States inferred by the inversion of NOx and VOC emissions by using satellite observation. During the last few decades, a number of nationwide regulations have been implemented to reduce ozone and its precursors. The substantial reduction in ozone precursor emissions may induce substantial changes in the ozone chemical regime. The identification of the ozone chemical regime is essential to determining the effectiveness of ozone control policies. Therefore, numerous studies have employed the satellite-derived formaldehyde to NO2 ratio as an indicator for ozone NOx VOC sensitivity and numerical modeling. However, recent studies have reported satellite-observed NO2 and formaldehyde columns do not necessarily reflect a trend in the NEI emission and air surface air quality. For NO2, the contribution of background sources of NOx in the atmosphere has increased recently. Those are majorly from lightning and soils. For formaldehyde, the trend in urban cores is consistent with the trend of NEI emissions. However, biogenic and biomass burning emissions are mostly driven by temperature, and those emissions are dominant over the southeastern and western United States in the summertime. Also, CTM is very useful to connect column and surface air quality and identify the response of ozone to the precursor emissions. The uncertainty of emission inventories often cause significant bias in the result of model. To resolve these issues, we applied an analytical inverse modeling technique with the OMI, NO2, and formaldehyde column retrievers to estimate top-down NOx and VOC emissions over the columns in the summers of 2011, 2014, and 2017, with proper consideration of background sources to the upper troposphere. From adjusted emission, we examined changes in the ozone chemical regime over the columns throughout the study period. In this study, we used the CMAS DDM 3D model developed and released by the EPA. We used CP6 and ARO6 mechanism. Meteorological variables are simulated by BURP. Details regarding model configurations are shown in this table. The emission data, which is the prior emission in this study, is comprised of anthropogenic, biogenic, lightning-induced, and biomass burning emissions. OMI has provided nearly continuous daily column retrievals since 2004. For this study, we used tropospheric NO2 and total formaldehyde columns, Level 2 and version 3 products. We applied quality filtering and replaced prior profile of OMI with that of CMAS simulations of this study. This figure shows the spatial distribution of seasonally averaged NO2 and formaldehyde columns from OMI for the summers of 2011, 14, and 17. For NO2, there are high values over major cities. During the study period, NO2 column has been decreased by 6 to 8% in domain-wide. For formaldehyde column, high values are dominant over the southeastern United States, which is driven by isoprene oxidation from biogenic emission sources. In this region, formaldehyde column consistently decreased in 2014 and 17 compared to 2011, up to about 34%. Before conducting emission adjustment, we examined changes in NO2 and formaldehyde column retrievers and the contribution of background sources to the upper troposphere. We showed OMI columns with the MS factor adjustment, as well as CMAS output with different background setup over the entire columns, urban, rural regions, and southeastern area. We defined the urban and rural regions based on the U.S. census-based surrogate and the location of power plant. We applied 3 CMAS background setup with the prior emissions to see the contribution of background sources to the upper troposphere. First one is with the profile boundary conditions and without lightning-induced emissions. Second one is with dynamic boundary conditions, which is from hemispheric CMAS simulation with seasonal scaling with multiple satellite datasets and without lightning emission. The third setup has both dynamic boundary conditions and lightning-induced emissions. In general, CMAS underestimates NO2 column and overestimates formaldehyde column everywhere over the corners. For NO2 column, the trend of OMI NO2 shows a decreasing trend in the urban regions, which is caused by continuous effort to reduce NOx emissions. But in rural regions, the NO2 column were steady through the study period, which is possibly explained by the increasing contribution of non-anthropogenic sources that compensate for the reduction in anthropogenic emissions. We found that the addition of dynamic boundary condition and lightning emission is helpful to reduce model bias, dominantly in both rural and southeastern area. Compared to dynamic boundary conditions, lightning-induced emissions is more beneficial in this area. OMI formaldehyde column shows steady decrease except for rural regions, but it may overestimate the formaldehyde column by up to 57%. The discrepancy between the OMI formaldehyde column and the modeled column were the most significant over the rural area. Possibly instrumental noise of column retrievers and uncertainty of emission inventory, such as fire emissions, can be the reason. We then compare the NO2 and ozone concentrations with the aircraft measurement during the NASA Discover AQ 2011 and 2014 campaigns. The CMAS with the profile boundary conditions without lightning emissions, which is green color lines here, under predicted NO2 and ozone in the upper troposphere, which is common tendency of regional transport model. With the lightning emissions and dynamic boundary conditions, which is red colored line, model performance greatly improved above 2.5 kilometer height. This better model performance in the upper troposphere could prevent the misalignment of emission adjustment. In order to estimate top-down NOx and methane VOC emissions, we apply the Gauss-Newton method, which is an analytical inversion approach to finding solutions. The inversions with the Newtonian iterations gradually approach convergence at the zero of gradient of this cost function. Posterior emissions can be estimated by using the second equation. This figure shows the spatial distribution of simulated NO2 and formaldehyde column densities with prior and posterior emissions corresponding to the OMI observations, as well as their differences. We found that nationwide increases in NO2 column and decreases in formaldehyde column over the southeastern United States, resulting in significantly mitigated the discrepancy between satellite observed and modeled columns. We also found increased NOx emissions and NO2 columns in Mexico and Canada area, which is turn potentially enhance the influence of ozone precursors transported from outside of the corners. In addition, we observed enhancement of formaldehyde column over the northwestern United States with the posterior emissions possibly related to open fire events. However, the magnitude was relatively small. To avoid misclassification of the ozone chemical regime, we defined the threshold values by using the CMAS model with top-down estimated emission inventory based on the year 2011. We observed the response of surface ozone concentration to 20% of emission perturbation, along with modeled formaldehyde to NO2 column ratio for the revisit time of the OMI satellite. In order to find threshold values of the chemical regime, We plotted the cumulative probability of NOx-limited and NOx-saturated conditions with respect to formaldehyde to NO2 column ratio by following Jia et al. 2017. According to the result, formaldehyde to NO2 ratios of 1.6 and 2.6 are determined as resin threshold in this study. Where the ratio is lower than 1.6 as NOx-saturated resin, where the ratio is greater than 2.6 as NOx-limited resin, in between was defined as transition resin. This figure shows the spatial distribution of averaged ozone chemical production resin over the cones in the summer of 2011. Several metropolitan areas were categorized as NOx-saturated and transition resin, whereas the remaining rural areas were classified as NOx-limited resin. And this bottom figure shows the difference of formaldehyde to NO2 column ratio between 2011 and 2017. The column ratio in rural area decreased by -1.3 plus minus 1.71, mostly over eastern and southeastern United States. This resin modification toward the NOx-saturated condition could be majorly explained by the sustained decrease of formaldehyde columns as a response to the decrease of air temperature throughout the study period. Here we plot the spatial distribution of ozone chemical resin over these 5 boxes for the summers of 2011, 14, and 17. As a response to reduction of NO2 columns in urban regions, which was deeper than formaldehyde, the clear shift of the ozone chemical resin from NOx-saturated to transition or transition to NOx-limited were found partially over metropolitan areas like Seattle, Houston, and Pittsburgh, or completely even and over, of course, Houston and San Francisco, especially from 2014 to 2017. By contrast, Los Angeles and New York and Portland were the cities steadily remaining in the NOx-saturated resin throughout the study period. This figure shows changes in the ozone chemical resin for 12 main cities over the cones according to the distance from the urban cores and urban cores. The upper panel is for the cities in the western United States, and bottom panel is for the cities in the eastern United States. In general, cities in the western United States, except for LA, shows resin transition toward the NOx-limited conditions. However, the cities in the eastern United States, they tended to stay in the same region they were in 2011, or even came back to the NOx-saturated condition. Interestingly, we've also found significant changes in the location of resin transition. Particularly Chicago is the city that shows greatest changes in the location of resin transition from NOx-saturated to transition resin over toward the urban cores by 14 km, while the ozone chemical resin at urban core did not show any significant difference during the study period. In this study, to investigate the changes in ozone chemical resin over cones with accurate knowledge of concentration of its precursors, we applied the inverse modeling technique with the OMI and the NO2 and formaldehyde columns. Results show that gradual spatial changes in the ozone production regime and apparent shift from NOx-saturated to transition regimes or transition to NOx-limited regime over most of major cities in the western United States. In contrast, rural areas in the southeastern United States, it shows a decreased formaldehyde to NO2 column with a significant reduction in formaldehyde column driven by meteorology. The results of this study show that incorporating satellite observation into numerical modeling could be helpful to implement appropriate emission control policies for ozone air quality in time. Thank you.